Welcome to our session in quantitative methods, where we'll be discussing analysis of variance. So analysis of variance, popularly known as ANOVA, is a popular tool that is used to investigate how the variations between 3 and more means are found. So ANOVA is very important because it is used to test the differences that exist between 3 and above means. ANOVA is used in a lot of instances. There's what we call one-way ANOVA and a two-way ANOVA. The table that is used in analysis of variance is called the F distribution table. This one is used to test the hypothesis that the variance of one normal population equals the variance of another normal population. The second use of the F distribution mainly involves analyzing the variance techniques. So if, for instance, you have 3 marketing officers that you are considering promoting who have the same car, same capacity of people they are marketing to, you would want to test which of these marketers we want to promote. Given the same conditions of service, how is it that this marketer is able to produce so much sales than the other? So you can use what is called analysis of variance to test whether there's a difference in their mean sales. So there are 3 basic assumptions that ANOVA thrives on. Number 1 is that there are 3 or more populations of interest that are normally distributed. Number 2 is that these populations should always have equal standard deviations. Number 3 is that the samples from which the populations are selected are 1, they are randomly selected. Number 2, they are independently selected. So ANOVA can bestly be illustrated by an example given as follows. We have 3 people in the sales department, Ms. Banda, Mr. Mwenya, and Mr. Senga. So each of these ones have the following sample means. So we want to see, should we promote this man over this, or this man over this Mr. Senga? We can use their sales to calculate. Now, ANOVA is part of hypothesis testing, and the procedures that are used in hypothesis testing will be used in here. The first one is, number 1, we need to state the hypothesis, where the now hypothesis will simply stipulate that there is no significant difference amongst the mean sales of the 3 salesmen. Or you can simply say mu1 is equal to mu2 is equal to mu3, just to imply that the mean sales of the 3 guys is the same. Our H1 or HA is what we call the alternative hypothesis. This alternative hypothesis simply could state that at least 1 is different. Or you say mu1 is not equal to mu2 is not equal to mu3. So the second step is to state the level of significance. Whenever you're not given, the standard is 0.05. The third step is actually to calculate the test statistic. Of course, in this case, we're going to use the ANOVA table that I'll explain later on. Then we make a decision based on the decision rule. So the ANOVA table for the F distribution, it's slightly asymmetrical, but it looks like this. This is the F distribution. So the rule is simply the same. If our answer falls within here, we accept. If our answer falls within the region, it's a rejection region, we reject. So the only difference that we're going to have in this case will only be in how to read the table. I'll take you through what we call the analysis of variance table. So we have what we call the ANOVA table, which has three sources of variation. Number one, the variation that comes between the treatments. Number two, the variation that comes between within the treatments, which is the error. So we have sum of square treatment, sum of square error, and sum of square total. Then this column is for the degrees of freedom. K minus 1 is the degree of freedom for the treatment, where K stands for the number of treatments or columns. Then N minus K stands for the degree of freedom for the error. So when you divide this degree of freedom for the error into the degree of freedom, when you divide the degree of freedom for the error into the sum of square, we get what we call the mean square error. When you divide the degree of freedom for the treatment into the sum of square treatment, we get what is called the mean square treatment. So this looks a little bit confusing, but it's very easy. I'll try to demystify it. So all these formulas you're seeing here can be summarized as follows. So a one-way ANOVA has information coming from one direction. There's one title. So this is a one-way ANOVA, and this is also a one-way ANOVA. A two-way ANOVA has two titles, one coming from the columns, which are denoted by K. K is the number of columns, which are treatments. The N, or B if you want, is the number of blocks. So these blocks here are 4. The total number of elements is called our N. Total number of elements here is our N, which is 12. So here, what is our K? We have 3. What is our N? There are 10 in total. What is our K? Here it is 3. So we have 3 columns. All right. So SS stands for the sum of squares. MS stands for the mean of squares. DF stands for the degree of freedom. Then treatment is denoted by the letter K or T. The blocks is denoted by the letter B or N, small n. The capital N stands for the number of elements. So I'm going to take you through this mini one-way ANOVA table where we have the sources. We have treatment, block, error. So whenever we have a block, this becomes a two-way ANOVA. For instance, this is typified by a two-way ANOVA because titles are coming from here and from there. So using this data here, we have 1, 2, 3, 4 columns. These columns are denoted by the letter K. So this is called our K. Then we have the rows here. We have 1, 2, 3. This is small n. So these are our what? Our blocks. Then we multiply this by that. We have capital N, which stands for the total number of elements. So far, are we together before I go any further?
Yes, we are.
Okay, so now that we are all together, this is a table that I need you to master. So this is sum of square treatment, sum of square block, sum of square error. Here, this is sum of square total. The degree of freedom for the treatment is K minus 1. Degree of freedom for the block is N minus 1. The degree of freedom for the error is N minus 1 times K minus 1. You multiply these two answers. Then we get our N down there. When we divide the degree of freedom for the treatment into the sum of square, we get the mean square. This answer into there, we get the mean square block. This answer into there, we get the mean square error. Then finally, when we divide the mean square into each of these ones here, we get the F calculated for the treatment, F calculated for the block. So I'm going to give you a hypothetical example. So here our sum of square treatment is 30, we put our 30 there. Our sum of square block is 30, we put our 30 there. Our sum of square total is 120, you put the 120 here. So the error is simply the difference. So when we add 30 plus 30, 60. We subtract it from 120, the remainder is our 60. This is called our sum of square error. For the treatment, it is k minus 1. So how many columns we have? We have 4. We're given here. So 4 minus 1 is 3. So when you divide this 3 into 30, we get 10. This is called our mean square treatment. Okay, let's go to the blocks. How many blocks do we have? 1, 2, 3. We're given here as 3. The degree of freedom for the block is n minus 1. So we have 3 minus 1, it is 2. So when you divide the 2 into 15 into 30, we get the 15 there. The acronyms stand for the variables that are being given. So this is MSB, the mean square block. When we multiply the 3 times the 2, we get our 6. So when you add all these, we're going to get our n as 11. Alternatively, n is simply sum of square is n minus 1. So when subtract 12 minus 1, you still get the same 11. Then this 10 now, we divide it into each of these ones. 10 into 10 is 1. 10 into 15 is 1.5. That is how we balance up that table. That is how we balance up that table. So balancing up the ANOVA table is very important because even without me teaching you how to find the other values, you'll be able to understand where they're coming from. So this one has two titles, here and there. I'm not going to take you for now on how we calculated the figures. I just want you to give me where the figures are coming from for each of the respective answers. So if we're given this one, sum of square treatment, this one, sum of square block, and this one, sum of square total. Can somebody tell me how do we find the sum of square error? Simply add this plus that, we subtract it from the total, the difference in here, which is 76. All right. Then the 3 here, the treatments. How did we get the treatments? Obviously, the treatment there should have been 1, 2, 3, 4. There are 4 what? There are 4 columns. So our K here is 4. And how many blocks do we have? 1, 2, 3, 4, 5. There are 5. So small n is what? 5. So when we go to our ANOVA table, we're going to discover that this is coming from 4 minus 1, which is 3. This is coming from 5 minus 1, which is 4. When we multiply these two, we get our 12 here. This is the 12 we are getting. So when you add all these, we get the total, which is 19. So when you divide this answer in there, we get 89. 4 into 26 is 6. 12 into 76 is 6.3. So now to get the F calculated, we divide this into there. We get the F calculated for the what? Treatment. Again, we divide this into there. We get the F calculated for the what? for the block. So this is how the two-way ANOVA is actually computed. Now, let me take you to a one-way ANOVA. Because the two-way ANOVA is tougher, a one-way ANOVA is easier. If you understand the two-way ANOVA, it'll be easy for you to understand the one-way ANOVA. So the format for a one-way ANOVA is simply sum of square treatment, sum of square error, then sum of square total. Here is k minus 1. This is n minus k. And divide this in there, we get our mean square treatment. Divide this in there, we get our mean square error. Then the f calculated is simply when we divide our mean square error into the mean square treatment. So I'm going to give you a hypothetical example. Suppose we have A, B, and C. Here we have 1, 1, 1, 1, 2, 1, 1, 1, 4. And here we have 1, 1, 1. That's for lessons purposes. Then we are told that our sum of square treatment, SS treatment, if what we calculated was, for instance, 20. What we calculated was 20. Then our sum of square total, suppose this was total here, we have 36. Let's balance this one up together. So what do we put here on the total? 36. What do we put on the treatment? 20. Now I want you to come in. The sum of square error, what do we have? Okay, let me change this here to 56. So we have something here, 56 here. So how do we find the sum of square error? Anyone? Matesho, how do you find sum of square error? The difference. Show people in their offices. So 56 minus 20, we get what? 36. Then here it's k minus 1. K here is the number of columns we have. So 3 minus 1, we have a 2. So 2 into 20, we have 10. This is called the mean square treatment. And here n minus k is what? The degree of freedom for the error. So n here stands for the total number of elements. So our n here is what? 12. So 12, when we subtract 3 minus 12 is 9. When you total this up is 11. So 9 in there will be 4. So to get the f calculated for this one, we divide 4 into 10, which is 2.5. So this is how we find our f calculated. This is how we find our f calculated. Now, it all starts from balancing. If you're able to know how to balance, it becomes easy for you to understand how to calculate it, because once you're able to know how to balance, the rest becomes easy. I gave your colleagues who attended this first class this small homework here. An exponent has been conducted for 4 treatments and 8 blocks. So meaning we've been given some data there. Complete the following analysis of variance table. So what is our K? What is our K? 4. Both treatments are denoted by letter K. And what is our N?
8.
8. So how do we find the error here? It's a difference, isn't it? Because the total must add up to 18. So 9 plus 4, we get 13. So the difference from 18 is what? 500, isn't it? It's 500. Are we together? So here, our degree of freedom for the treatment is K minus 1. So what are we going to put here? 3, since we're subtracting 1 from the 4. So 3 into 900 is 300. Then here it is N minus K. So our capital N. So if there are 8 blocks and 4 treatments, our capital N is simply when you multiply these two to get 30 what? 32. So how do we find the degree of freedom from the blocks? It is small n minus 1. So what is our n here? 8. 8 minus 1, 7. Then when we multiply these two, we get 21. So the total of everything here, we'll just subtract 1 from the n there, which is going to give us 31. Then to get the mean square for the blocks, mean square block, we simply divide the degree of freedom for the block into the sum of square. So we divide 400, sorry, divided by 7. So you get 57.14. 57.14. Okay. Then we divide 500 divided by 21. Here you're going to get 23.8. Okay. So to get the F for the treatment, we're simply dividing 300 divided by 23.8. 300 divided by 23.8. So here we're going to get 12.6. A Twoway ANOVA has 2 F calculated. A Oneway ANOVA has only 1 F calculated. So here we're 57.14. We divide it by 23.8. So we're going to get 24. So this is the F calculated for the treatment and F calculated for the blocks. So the procedure is simply the same. So when you're reading the F table, we use what we call the degrees of freedom. So to read, we're going to compare 12.6 using the coordinates 3, 21. Then to compare 24 against 7, 21. So it's a degree of freedom for the treatment against the degree of freedom for the error. The error is a starring in this case, because we use the error to divide in each of these ones to get the F calculated. Also, we use the coordinates against the error. So when you're reading this, the error will be in the what? A horizontal axis. Then here we're going to have the treatment, and here we're going to have the block as well. when you're reading the table, so where they're intersecting. So since this is at 0.05, we will need to check on a 5% table, and 5% table under 3.21 and under 7.21. So here we check the F tables are 3. There's a 5% here. There's another F table which has 1%. There's also one which has 0.1. So you need to be careful. In this case, the percentage is part of the title. So we're going to use a 5% table. So in the horizontal axis, there should be what? 21. Then here we got 3 and 7. So meaning where they're meeting here, 3.07, and here 2.49. So 3.07 and 2.49. So this is now where we're going to now put the figures there. 3.07, 2.49. So this one we compared against 3.07. And this will be under 2.49. So we always reject when the F calculated is greater than the F from the table. So 12.6 is more than that, we're going to reject. 24 is more than 2, we're also going to reject. You need to understand that each time we're rejecting, it means there's a significant difference in the means. Whenever we are failing to reject, there is no significant difference in the means. So basically this class is just to teach you how to balance up the tables. So I'll need you to try to come up with an ANOVA table for question 3 and for question 2. One for question 3 and one for question 2. You have been given the figures already there, the sum of square, total, block, and the treatment. So unless there are any questions at this point, I'll end here and I'll ask you to continue this homework I'll send on the group. Thank you so much, and let's meet in the evening for the calculation.
Sorry, just sorry, just a question. Will you share the study material or?
Yes, I'll share the study material.
Okay.
Yeah.
Okay.
All right. Thank you.
Thank you.